Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the lecture 3 of module 8. I hope you have been enjoying all the lectures that happened so far. In the lecture today, we are going to continue with the composition of the mantle, and then we will briefly discuss about the composition of D double prime layer as well. And finally, we will be having the summary of today's lecture. As far as the recap of previous lecture is concerned, we learnt about the geotherm, which is basically the temperature variations with radius in the earth, and the geotherm depends on the sources of the heat and the modes by which the heat is transferred upward in the earth, and an average thermal gradient is 13 degrees C per kilometer, that is up to the depth of 100 kilometer, after which it has a adiabatic process where the temperature increases very slowly, and thereafter we do have a high thermal gradient at the D double prime layer. So the low gradient in the middle mantle is about 0.6 degrees centigrade per kilometer, that is up to the base of the mantle. Higher temperature reduces seismic velocity and its strength but increases attenuation. Conversely, higher pressure increases the velocity and its strength but reduces attenuation. This means if temperature increases, then the attenuation will also increase, but in the case of pressure, if the pressure increases, then attenuation will reduce. Temperature increase rapidly in D double prime, as I told you previously, and that causes velocity to go slower than expected from the lower mantle velocity gradient. So if we compare the thermal gradient of the upper mantle, that is maybe up to 100 kilometer, and the D double prime layer, then both have almost more or less similar to each other, the thermal gradient. And in the D double prime layer, because the gradient is too high, so it basically reaches to the solidus, but it doesn't touch it. The high temperature in the core keep the outer core liquid, but the rapid increase in pressure due to the weight of the outer core makes the inner core freeze into a denser solid. A key result from the experiment is that the bulk, sound speed and the density for a material are approximately linearly related for a given mean atomic weight. So if you remember, we had a graph where we had the bulk sound speed phi to the power 1 by 2 on the y-axis, and there we had the density of the different minerals. So those were linearly related, and then we checked for the mantle where the density is around 4.3, so it is mostly consist of the mineral dunite, and in the case of the core, that is mainly consist of Fe2SiO3, and that is on the left side of the pure iron. So dunite is rock containing 92% olivine, which in turn is 90% phosphorite. So there are two kind of rocks of olivine possible, phosphorite and fayalite, but the phosphorite is the one which is mostly abundant and around 90%, and that fits the mantle data. Crust is predominantly basaltic and or granitic depending on the continents or the ocean. Upper mantle mainly composed of peridotite, and it also depends upon the pressure variations that peridotite may form another minerals such as olivine, clinopyroxene, orthopyroxene, or maybe in the presence of garnet spinel or the plagioclase. The transition zone corresponds to a series of solid state phase changes where many phase changes occur, like from alpha olivine to beta olivine, then from beta olivine to the gamma. So that basically doesn't change the chemical composition, but the structure does change. The transition zone that basically has 2 to 3 discontinuities. One is present at 410 kilometer, another is present at 520 kilometer, and the third one is present at around 660 kilometer. And at these discontinuities, olivine changes to its various polymorphs depending upon temperature. So at 410 kilometer discontinuity, olivine changes to wetzelite, and at 520 kilometer discontinuity, wetzelite changes to ringwoodite, and then at 660 kilometer discontinuity, ringwoodite turns to perovskite and magnesiowustite. So perovskite, also known as bridgmanite, and that is the most abundant mineral in the lower mantle. So the lower mantle's main constituent is perovskite, which is known as bridgmanite, and also there would be a fraction of magnesiowustite and ferropericlase. Outer core is composed of iron nickel, that is also known as knife, NIFE knife. That means, that is for the sake of remembering it easily. So NIFE knife, so nickel iron alloy, and it lies at 2891 and 5100 kilometer. An inner core mainly composed of solid iron, and it lies at 5100 to 6400 kilometer. So what happens in the outer core? Because of the too high temperature, the material present in the liquid form. But as you go deeper towards the inner core, because temperature is still increasing, but the pressure increases much more than what the temperature is increasing. So because of the pressure increment, the material over there in the inner core is solid in nature, or you can say much more viscous in nature than the material in the outer core. So this is about the composition of the mantle. This is just you can say the simplified summary, but it is not for the for like everything, but it is just for having a like glimpse of what is the composition of mantle and what kind of the phase changes are happening in the mantle at 410 kilometer discontinuity, 660 kilometer discontinuity, and 520 kilometer discontinuity. So in the upper mantle, we have olivine, and that is basically of two types, like fosterite and phalite. And in the upper mantle, mostly the fosterite is present. So it has the alpha phase, and it is orthorhombic crystal system. And at 410 kilometer discontinuity, because the pressure is increasing and it reaches up to 12 gigapascal, then what happens? This olivine, that is of alpha phase, converts to beta phase, and it is a beta spinel cubic structure. So what is basically happening? The HCP structure, which is changes to the CCP structure from alpha phase to the beta phase, and this beta phase is basically spinel cubic in nature, and the temperature also keep on increasing. Pressure is increasing to 12 gigapascal. If you can understand that there is no change in the mineralogy, only the structure is changing. So you can say like the chemical formula is same for alpha phase and the beta phase, but their structures are different. One is orthorhombic, another one is beta spinel cubic structure. So the alpha phase is changing to the beta phase. So, or you can say the fosterite is changing to wetzelite at 410 kilometer discontinuity. As you go even deeper, the pressure keep on increasing, and the pressure increases to 15 gigapascal, and at that point the wetzelite changed to ringwoodite, which is gamma spinel. Still the chemical formula is same, but the structure is changing to gamma spinel. And thereafter, if you go even deeper structures, then at around 660 kilometer discontinuity, pressure increases to 24 gigapascal, and that ringwoodite will change to perovskite, or it is known as bridgmanite. And here also there is no change in the mineralogy, only the structure is changing. And this perovskite is the most abundant mineral in the earth. Around 70% of the lower mantle is comprises of perovskite, and this perovskite at the D double prime layer changes to post perovskite. And there is another mineral present in the upper mantle that as we have talked about in the previous lecture. There is pyroxene is also present, and that pyroxene below 200 kilometer, the because of the increase in the pressure changes to garnet, and then at 660 kilometer it changes to perovskite or the bridgmanite, and then this perovskite will change to post perovskite at D double prime layer. So this is what it is indicated in this particular mineral assemblages for the mantle, and it gives a much more uh, detailed view of what kind of composition is present at various depth into the mantle, at least up to 1800 or the 1800 kilometer depth. So upper mantle, as we have seen, is mostly comprises of olivine, and this basically goes into a series of phase changes at the transition zone, and the alpha phase olivine here will change to beta phase, and this beta phase will be beta spinel structure, and that is also called as wetzelite at a pressure of around 12 gigapascal, and this phase change happen at around 410 kilometer discontinuity, and then this beta phase transform to gamma phase, and this gamma phase is also having the spinel structure which is known as ringwoodite, and that happens at around 15 gigapascal pressure, and this discontinuity is present as 5.520 kilometer discontinuity. This is a less dramatic seismic discontinuity around which this phase transformation happens, and at around the pressure of about 24 gigapascal, this beta phase transform to gamma spinel, or you can say at 24 gigapascal, that means corresponding to 660 kilometer discontinuity, the gamma spinel turns to perovskite structure and also change to magnetio-woodsite structure, while on the other hand, the pyroxene component also undergoes various changes. So beginning with the transformation to garnet below around 200 kilometer, it also undergoes to the pyroxene goes to the garnet at around 200 kilometer, and that below 600 kilometer, the magnesium bearing garnet, that is majorite, transformed to a structure called ilmenite. So this is where it happens, and beneath 660 kilometers discontinuity, the majorite transformed to perovskite, and some of the majorite probably is still there, and into the lower mantle as a stishovite, a high pressure phase of quartz, and an Al2O3 rich phase. The pyroxene and garnet transformation occur gradually. So basically, if you look at the transformation and compare with the olivine phase transformation, the pyroxene and garnet transformation happens very gradually, and it contributes to a high velocity gradient through the transition zone down to around 770 kilometer. But if you look at the phase transformation of the olivine, that happens very suddenly, so in a very narrow depth range, that we will see in the next slide. And the velocity structure at the transition zone may still be benefited from the seismological study to understand its composition, and there are basically two possibilities for the phase changes at the transition zone. There is case 1, that is the univariant phase change, and there is case 2, that is the complicated multivariant phase change. So there, in this particular section, you are seeing the simple univariant phase change in which the material of a single composition completely changes from one phase to another. So this is where the phase is changing from alpha to beta here, and this phase change is happening due to the pressure increase, and that basically forms a very sharp discontinuity here. So this is not a gradual change, it is the sharp change in the discontinuity, so that, or you can say the sharp change in the velocity. But on the other hand, there can be a possibility of complicated multivariant phase, and we are now here talking about the divariant reaction, where at a particular pressure and composition, both the phase alpha and beta are coexisting each other over a broad region of the pressure. So this is the region where both the phases are coexisting, and this will produce basically a velocity gradient. It is not a sharp change, it is a gradient over here. So basically we need to have much more sophisticated models of the transition zone using some kind of seismological data, or maybe benefited by some other kind of geophysical technique to understand the velocity structure of the transition zone. Here in this particular figure, relative proportion of the mineral phases in the upper mantle are shown. So if you look at, this is the volume fraction and this is the depth of the upper mantle is shown. So between around 0 to 410 kilometer discontinuity, there is a alpha phase of olivine, which basically changes to beta phase over a very narrow range of the depths. And while if you compare it with the beta to gamma phase change, the change is happening over a relatively broader depth range. So the change from alpha to beta is basically exothermic in nature and occur at lower pressures in basically subducting slabs due to the colder temperatures at 410 kilometer discontinuity. While on the other hand, from beta to gamma transformation occur at around 520 kilometer discontinuity, and that is a broader depth range. And if you even look at the gamma spinels, that changes to perovskite and magnesiowustite transition, that occurs over again around a narrow depth range, and that is consistent with the observed sharpness of the 660 kilometer discontinuity. And if we talk about the pyroxene, so this is the pyroxene curve here, and this pyroxene curve is basically occur the transformation very gradually, and this contribute to the high velocity gradient through the transition zone. So what you can observe, the transformation from alpha to beta is happening very suddenly, or you can say very sharp changes there, but on the other hand, from pyroxene to garnet, the change is quite gradual. So when we compare the composition of upper mantle versus lower mantle, there is a unresolved question, is whether the lower mantle is chemically distinct from the upper mantle, and which has important implications for how the two have mixed during the evolution of the earth. So the velocity data do not appear to require phase changes in the lower mantle. However, the lower mantle may be denser than expected for pyrrolite and hence perhaps enriched in the iron and silica. And the subducting lithosphere, as per the observation, penetrates the 660 kilometer discontinuity, that basically indicates towards the mixing has occurred. However, even if all the slab reach the lower mantle, the earth may not be old enough for the lower and upper mantles to be well mixed. Another possibility is that the early earth had distinct upper and lower mantle convection systems, and whole mantle convection began later. Now let's talk about the D double prime layer composition, which is the region that basically includes the lateral velocity variations, and there might be a presence of vertical layering and also the presence of anisotropy. So basically there are the processes that may be very complex in comparison to the lithosphere, and the other major thermal boundary layer, that is the lithosphere asthenosphere boundary, is present. And this complexity may reflect factors including subducted lithosphere, the generation of mantle plumes, and interaction between the core and the mantle. So, in order to understand the composition of D double prime, we can have three possibilities, and we are going to discuss about all those three possibilities. So, this is the model one, and as per this model, there might be a presence of simple convection model where a cold material is sinking into the core mantle boundary. So this is the material that is sinking down to the core mantle boundary here, and that material, after getting in contact with the core, gets heated up and then rise again over here. So the left side, this one is basically shows the resulting vertical velocity profile in the region of downwelling. So this is the downwelling region, this is the solid line, and this is the upwelling, that is the dash line. And you can expect large lateral seismic variation more than plus minus 5% at the base of the mantle, that would be caused by temperature variations. However, given the complex seismic structure observed, this model component seems necessary but insufficient. There is another model that was proposed, that the subducting slab is basically do not this subducting slab do not reach to the top of the core, but remain basically separated from the core by this particular layer over here. This is basically considered as drags, and this layer may result from early planetary differentiation or may have grown by chemical reactions between the core and the mantle. And high pressure experiment implies that the perovskite and the magnesiumite in the lower mantle would react with the iron, and these are the drags, might be thinned in the region of the subducting slab or the downwelling slab. Here it is thinner and here it is thicker under the upwelling arms. So layering in the drags may explain observations of transverse isotropy in the downwelling region. So here, because the layering is happening in the thinned region underneath the slab within the drag, so it may explain the transverse isotropy, while in this region, because the vertical sheets are present like this, so it may explain the upwelling region in terms of azimuthal anisotropy. The velocity increase of the D double prime discontinuity may be partly caused by the ponded slab material, which will still be colder and have higher velocity than the ambient rock. This discontinuity may be enhanced by drags flowing up. There is another possibility, that is for model 3, and it says that the part of the subducting lithosphere that has started as a basaltic ocean in the crust, then transformed into the eclogite, then to a material that is seismically faster than the rest of the lower mantle, and this phase could delaminate. So this phase basically delaminate from the slab and accumulate, forming a different chemical boundary layer, that is if it is remained solid, it might partially explain the D double prime layer. So basically the subducting slab is going down and it gets delaminated and accumulate at the core mantle boundary in the form of the post crust, and that can basically or partially explain the D double prime discontinuity. Alternatively, if it melts, this layer if it melts, it might explain the ultra low velocity zone that is also present at the base of the mantle. Either way, its laminar nature might explain the observed seismic anisotropy. The lateral variations in the velocity would correlate with anisotropy, as such waves would travel fast in the downwelling region because of the transverse isotropy, but be slowed by the vertical laminations beneath upwellings. So it may form the plume activity and comes back up again onto the surface. So this is the summary of the lecture today. The beta phase transform to gamma or spinel structure known as ringwoodite at a pressure of 15 gigapascal, corresponding to less dramatic seismic discontinuity at 5 to 0 kilometer. Gamma spinel breaks down to perovskite structure and magnesiosite at 660 kilometer discontinuity. A simple univariant phase change causes a sharp discontinuity in the velocity, while a complicated multivariant phase change produces a velocity gradient. So in the univariant, the sharp discontinuity is present, and in case of the divariant or the multivariant phase, both the phases are coexisting with each other and produces the gradual velocity changes. The olivine alpha to beta reaction uh, should occur over a narrow depth range, that is exothermic in nature, and beta to gamma transformation, that is endothermic in nature, should occur over a broader depth range, which agrees well with the lab prediction. While similarly for the pyrrolite, that when changes to garnet, then it has a gradual change. The gamma spinel to perovskite and magnesiosite transition should occur over a narrow depth range consistent with observed sharpness of the 660 kilometer seismic discontinuity. While for the D double prime layer, for four possible models, describes the observed characteristic. First is a simple convection model, cold material sinking to the core mantle boundary, heating up from the contact with the core and then rising again. Second model predicts that the subducted slab do not reach to the top of the core but remain separated by a chemically distinct layer. Another possibility is that the part of the subducted lithosphere that started as basaltic ocean crust then transformed to aclogite to a material that is seismically faster than the rest of the lower mantle. So this is the lecture today, and these are the references, and we are going to meet in the next lecture, lecture 4 of module 8. And thank you so much. Bye bye.